Hi everybody, welcome back. In this video, I will teach you about Lewis acids and bases, just give you a brief intro. But before that, let's review over the other two definitions that we've learned so far. So an Arrhenius acid produces protons in an aqueous solution. And remember, protons come in the form of hydronium ions. An Arrhenius base is defined as producing hydroxide ions in an aqueous solution. A Bronsted-Lowry acid is defined as a proton donor, and a Bronsted-Lowry base is a proton acceptor. And the Bronsted acid and base definition is the one that we're using throughout this entire chapter in series of videos to predict the products of reactions. But I wanted to introduce you to the Lewis acid and Lewis base definition. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Now these definitions are the most general definition. And in organic chemistry, you would go on and learn a bunch of different chemical reactions and their mechanisms. And it's all looking at the Lewis base attacking the Lewis acid. And we would call the Lewis base the nucleophile. And as the name suggests, it loves nuclei, but more specifically something that is electron poor. And so having kind of like a nucleus positive charge in a sense. So the nucleophile is electron rich, seeking something electron poor. And the electrophile is a Lewis acid. It's electron poor, and so it's looking for something more negative. Opposites are attracted to each other. So nucleophile to electrophile. And so this would be the most general definition that would apply to a vast majority of reactions that follow these polar mechanisms, not just a proton transfer like we've been studying with the Bronsted-Lowry acid and base definition. And so let's talk a little bit more what makes a Lewis acid a Lewis acid. Well, a Lewis acid has an empty orbital. Remember, orbitals are the places that electrons hang out in, right? They're like the apartments for the electrons. So Lewis acid has an empty orbital, or it can rearrange. I'm going to show you an example of both. Electrons to create an empty orbital. So move electrons around so we can create available space. And then that empty orbital is what can accept an electron pair, right? So that we can form a new bond. So the empty orbital from the Lewis acid can accept an electron pair. Another thing that would always help me to remember this definition is I look at Lewis acid and I see acid starts with A and acceptor starts with A. And so that always helped me as a student to remember Lewis acid is an electron pair acceptor. The only way it can accept an electron pair is if it has an empty orbital to do so, or can rearrange to accept the electron pair. So let's talk about molecules that act as Lewis acids. And remember, I'm giving a very brief introduction to this topic. This is a second semester general chemistry course. If you want to take OChem, you're going to see a lot of different Lewis acids. So just be mindful of that. So the first one I'm going to look at are the molecules that have incomplete octets. One example is aluminum chloride. And let's say we have ammonia added to it. Now we know these nitrogen, ammonia, and ammonia derivatives have electron pairs, and we've talked about that before in a previous lecture when we talked about bases, right? That lone pair is what will be donated, right? And so aluminum doesn't have a complete octet, so it does have space to accept this electron pair. I'm going to draw that in the green. So use the tail of the arrow to point towards, so from Lewis base to Lewis acid, it's always the direction we go in, to create this species here. If you were to calculate the formal charge for nitrogen, it'd be +1, for aluminum, -1. And so therefore, the aluminum chloride was your Lewis acid, and your ammonia was the Lewis base, the electron pair donor. Now, if you're taking my second semester general chemistry course, you're not required to show the electron flow. I just want you to be able to identify Lewis acids versus Lewis bases given the next species in the reaction. And so I think it's always helpful to visualize, well, what's actually happening with the electrons rather than just memorizing them. So that's why I wanted to show you that the Lewis base attacks the Lewis acid, right? This is electron pair being donated, and it created this bond between aluminum and nitrogen. If you do go on to take organic somewhere else, make sure, I always highly advise when I teach organic, I use different colors, and I always have that new bond in green so it just stands out and I can see like the movement of electrons. All right, another example that may come to mind, since first semester general chemistry, you may remember that the boron, kind of like species, this one I'm showing you, boron trichloride here, they don't have complete octets as well. So let's say I mix some diethyl ether in there. That oxygen has lone pairs that can be donated. Boron's like, hey, come on over here. I have space. I have an empty orbital. And so therefore, you end up with a species that looks like this. The oxygen has one lone pair left over. The other one was used to make the bond there and has a +1 formal charge, and that boron would have a -1 formal charge. So whenever you're drawing these, that's why I always find it helpful to draw out the electron flow, I see that these electrons were used to make the bond. So that's the reason why I knew that only one lone pair was left over. We know an oxygen with 3 bonds and one lone pair has a +1 formal charge. And then the boron would have a -1 formal charge to give an overall neutral. So, seeing that the boron species accepted an electron pair, we would identify it as a Lewis acid, and therefore the diethyl ether was your Lewis base. Now, some molecules that may not initially contain empty orbitals, like not have incomplete octets, can still rearrange and act as Lewis acids. So let me show you an example here. Let's say we have carbon dioxide and water. Now this is where it is really helpful. Let me find a different color. I'll do orange. Where it's really helpful to know your electronegativities. You can identify polar covalent bonds quickly and assign partial positive and partial negative. So when I look at carbon dioxide, I know these oxygen atoms are electronegative. So I assign partial negative, and that this carbon here is partial positive. Even though overall the molecule itself is nonpolar, we do understand that that carbon atom in the center there is electron deficient. We also know that this oxygen atom in water is partial negative, and then these hydrogens are partial positive. So opposites are attracted to one another. Always, always is your mantra in chemistry. So these two oxygens don't like each other. They're not going to want to attack each other, right? And so what's really wanting to attack here is this oxygen, and it's really attracted to the carbon in carbon dioxide. And so even though it looks like carbon, its octet is full. It's like, I'm done, but it can rearrange to accept that lone pair of electrons. So let's see how it happens here. So these electrons come here, they attack that carbon, and in order to obey carbon's octet rule, remember no more than 4 bonds to carbon, not going to happen, then it's going to break one of these bonds in the double bond and push those electrons and make them into a lone pair onto the oxygen in order to house in that water here. Now, it doesn't matter which one of these double bonds you would have chosen here, right? Because it's going to attack, it could attack either way, right? So, since there's symmetry, let's draw the species that we have. And that oxygen from water still has 1 lone pair, so we'll draw it in. And now we have a bond between oxygen and carbon. Carbon still has a double bonded, still has that carbonyl there. But then the other oxygen, this bond broke, turned into a single bond, and now it has an oxygen with 3 lone pairs, like so. Now the formal charges. Oxygens with 3 bonds and 1 lone pair, you can calculate the formal charge, but it's +1. Oxygen with a single bond but 3 lone pairs has a -1 formal charge. So this is what this intermediate looks like here. But then these molecules can rearrange intramolecularly. So what's going to happen is this oxygen here is like, hey, I see you have a proton, and I want to minimize my formal charge. So it grabs that proton, these electrons break, and then go from a shared pair of electrons to a lone pair of electrons. And you end up with this oxygen having 2 lone pairs now. This carbon still has that carbonyl, but now this oxygen has 2 lone pairs and a hydrogen on that side. And this is actually the structure for carbonic acid. Now, don't stress. You're not required to know this type of mechanism just yet. Just wait for OChem then. But I wanted to illustrate to you a lot of the principles you're learning in general chemistry, like assigning partial positive and partial negative charges, and understanding that opposites are attracted to one another, and obeying the octet rules. Like, all of these principles build the foundation so that you will be able to do this later on if you elect to choose to take organic chemistry as part of your STEM pathway. Okay, so that's why I wanted to show it to you. I know it's a little bit advanced, but hopefully it gives you kind of a picture of what's to come down the road. And like I said, how useful it is to have this information strong and build that foundation so that you are successful in OChem. So therefore, coming back to general chemistry expectations here, since the carbon dioxide accepted the electron pair here, it will be identified as your Lewis acid. So it's not as obvious as aluminum or boron species where like they clearly had didn't have an octet, so they had an empty orbital available. This one, you would have to look at what the next species was. And it's like, oh, well, I see the oxygen's attached to the carbon, and the only way that happens is that oxygen has that lone pair to donate. So you just have to look at what is formed. Therefore, water is behaving as a Lewis base here because it's donating an electron pair. And then I just wanted to finish up the mechanism for you. You can, almost identify this part of the molecule as a Lewis base or nucleophile, and then this part as the Lewis acid. It's accepting an electron pair, and that's the electrophile, but you won't be responsible for intramolecular rearrangements in this course here. All right. Finally, there are cations that can act as Lewis acids as well. And so just like on their own, and we've seen that before a little bit in a previous video when I talked about aluminum and how it was in the video where I discussed how cations can act as weak acids and ionize water to a small extent. So this is the formation of that coordination compound. So we have 6 waters. And therefore, aluminum will coordinate. It's not true bonds here, they're coordination bonds, which you would discuss in an advanced inorganic chemistry course. More of those types of materials. But hopefully this one's a little bit more straightforward, where you see that aluminum is electron deficient. It has a positive charge, so it has to accept electron pairs. And then you can see water is a great Lewis base because it has lone pairs available to donate. So you're going to see oxygen species, nitrogen species. They're great Lewis bases, especially if they're partnered up with some sort of transition metal or aluminum cation. Like, they all have a positive charge and empty orbitals to house other electron pairs. All right, so let's work a problem together so you can see what could be asked of you on an assessment. The first one, we have a silver cation plus ammonia to give this complex ion. And, a lot of times I like to draw the Lewis structures like ammonia. So I would draw that out and say, okay, I know ammonia looks like this with a lone pair. So you're always kind of like hunting for the lone pair. In addition, you can see here that silver has a +1 charge. It's a cation, so it has to act as the Lewis acid. And then once again, recognizing the fact that ammonia has a lone pair here, it's definitely going to be able to donate that lone pair. And therefore, ammonia is a great Lewis base in this example here. All right, the next one, we have fluoride. So if we were to draw the structure of what fluoride looks like, wow, there's a ton of electrons to work with here. It also has a negative charge, which is also a big clue that it's going to be a Lewis base or a nucleophile if we were using the organic terminology here. And we've seen the boron species, if we were to draw the Lewis structure, boron has an incomplete octet, and so it welcomes that fluoride in. So that fluoride can come in and attack the boron here and then make the BF4 minus. So therefore, our Lewis base is the fluoride, and our Lewis acid electron pair acceptor is the boron trifluoride species. All right, so thank you guys for watching, and I will see you next time.